Ionic compounds, giving and taking of electrons. You'll notice we have two labels, cations on the left, listed in orange, and anions on the right, listed in blue. Cations are positive, anions are negative. The cations will be positive 1 for the group 1 metals, the first group. This is because they give up their 1s electron. The second column, the group 2 metals, will have a positive 2. It gives up both electrons that are found in the s block. We skip over the transition metals, and the third block, the 13th group, starting with boron, has a positive 3 charge because it's giving up both s electrons and the 1p electron that it currently has. The fourth column, or the 14th group, will have a positive 4, giving up 2 s electrons and 2 p electrons. In the transition metals, we have a hodgepodge of charges. The reason for this is because we have the d and the f block. These electrons might slide out, or electron configurations might change that allow them to surface. This will allow them to interact with other atoms. For the anions, we have a negative 4 charge, a negative 3 charge, a negative 2 charge, and a negative 1 charge. This is because it's easier to recruit new electrons from neighboring atoms than it is to lose electrons. So rather than losing the s and the p electrons that they have, they will gain additional p electrons. Here are the rules for naming ionic compounds. Number 1. Name the first ion followed by the second ion. Number 2. Change the ending of the second ion to "-ide" unless it is a polyatomic ion. The third step is conditional. If the cation is a transitional metal with multiple oxidation states, write the Roman numeral indicating the oxidation state, or the charge, in parentheses after the metal name. Roman numerals typically go between 1 and 8. I, II, III, IV, V, VI, VII, VIII. Roman numerals are not applied when only one oxidation state exists as an option, so group 1 and group 2 metals never receive a Roman numeral. It's unnecessary. If you run into trouble, remember, divide the two ions with a pencil or mentally. Remember, polyatomic ions are usually anions, so the division will typically happen after the very first element, which is going to be a metal. Check to see if it is a transition metal, and check to see if it has multiple oxidation states. If it does, then you'll be using a Roman numeral. If not, it should be in one of the groups that allows you to know the charge immediately. We're going to try to do 10 of them. We're going to be very systematic about it. So we're going to do Rule 1 first. We'll name them. Copper. Second one starts with magnesium. Next one with iron. Next with magnesium. Next, sodium. Next, sodium. Next, barium. Next, copper. The ninth one has parentheses around the very first one. Parentheses are a strong indicator that we have a polyatomic ion. This is the only one that you have to worry about that is a positive cation. This is ammonium. And finally, we have calcium. Next, we'll go through and we'll add the second ion. Now, because ending changes will occur, I'm only going to leave the first portion. So we have chlorine, and I'll write chlor. We have oxygen, and I'll write ox. Oxygen again, so ox. SO4 is sulfate. It is a polyatomic ion. I will write the full name. The next one is dichromate. It is a polyatomic ion, and so the whole name gets written. The next one is hydrogen carbonate, again a polyatomic ion. It can also be called bicarbonate or bicarbonate. Next we have sulfite, again a polyatomic ion. Next, another polyatomic ion highlighted by the parentheses of nitrate. Again, another polyatomic ion. This is phosphate. And then finally we have oxygen again, so I'll write ox. Now I'll sweep through and change the ending of the second one to "ide." Because I've left only a portion of the name, I simply am going to finish it up. You can see all the polyatomic ions remained the same, and there was no need to change them. The third rule was conditional. I'm going to go through and check to see all the ones that were transition metals that may have had multiple oxidation states. Copper, iron, and copper again are the only ones that have multiple oxidation states. Also, if you look carefully, they're the only ones that were transition metals here. Now, copper chloride is going to be copper 2 chloride because chlorine has a -1 charge, and I have 2 of them. With only one copper, that copper must have a +2 charge. With the iron, oxygen is in a position that it has a -2 charge. I have 3 of them. 3 times -2 is -6. I need to have a +6 coming from all of those irons. 6 divided by 2 is 3. So this is iron 3. With the copper nitrate, again, we're going to end up with copper 2. This is because nitrate, like the chlorine, has a -1 charge, and we have 2 of them. So 2 times -1 is -2. I'll need a +2 to counteract that. Since I only have 1 copper, that 1 copper must have a +2 charge. Writing an ionic formula from a name. First, write the symbol of the first ion, and then the second ion. Include the charges of each. The cation, or the electropositive one, will always come first. Then we'll have the anion, the most electronegative one. With the charges in place, we'll crisscross the charge values, ignoring the charge sign. So we could very well erase positives and negatives, or just simply mentally ignore them. When we crisscross, we're going to bring the superscripted charge, number, down to the subscripted quantity. So we'll go ahead and do that. And then if necessary, we will reduce to the simplest whole number ratio. If there are multiples of any polyatomic ion, then the polyatomic ion must go into parentheses with the quantity or the subscript on the outside. Let's go ahead and try 10. We'll systematically go through these, so I'm going to list all of the cations first, the positive charge. Calcium with a +2, magnesium with a +2, iron 2 has a +2 charge, sodium +1, tin 2 with a +2 charge, lead 2 with a +2 charge, ammonium with a +1 charge, nickel 3 with a +3 charge, lithium with a +1 charge, and aluminum with a +3 charge. I'll then sweep through and add in the anion. We have chlorine with a -1 charge, sulfur with a -2 charge, nitrogen with a -3 charge, chlorate. The ATE ending really strongly indicates that I should look at my polyatomic ion sheet, and I find ClO3 with a -1 charge. Next we have fluorine with a -1. Nitrate, the ATE ending, sends me to my polyatomic ion sheet, where I find NO3 with a -1 charge. Hydroxide, while it ends with IDE, it's strongly suggested that you learn hydroxide and cyanide as polyatomic ions. We find it on the polyatomic ion sheet with OH with a -1 charge. Nitrate again is NO3 with a -1 charge. Hydride is hydrogen with a -1 charge. And hydroxide again with a -1 charge. We go ahead and we crisscross. CaCl2 for the calcium chloride. Magnesium sulfide becomes Mg2S2, but since that can be simplified, it becomes MgS. Fe3N2 for the iron 2 nitride. NaClO3 for the sodium chlorate. SnF2 for the tin 2 fluoride, Pb parentheses NO3 close parentheses 2 for the lead 2 nitrate. Notice there are multiples of the polyatomic ion, so it had to go into parentheses so no one thinks that we've got 32 oxygens for every 1 nitrogen. Ammonium hydroxide, NH4OH, Notice the H's do not come together, so we see a very clear separation of the ions. Ni parentheses NO3 close parentheses 3 for the nickel 3 nitrate. No one wants to think we've got 33 oxygens for every one nitrogen. Lithium hydride is LiH, and aluminum hydroxide is going to be Al open parenthesis OH close parenthesis 3. Again, it's a polyatomic ion that there are multiples of, and therefore must have parentheses around it, so no one thinks that there's one oxygen for every 3 hydrogens. Instead, there are 3 OHs.